Hello everyone. I would like to thank the organizers for inviting me to give this talk here. So I'm gonna, if this works, I'm gonna start with how we make the devices and how we design the setup to measure them. And then I will change a little bit my talk to what it was intended. I will very quickly go through some of the highlight studies we did on stability. And I think will be more interesting to the audience to focus on the third part, which is some of the procedures we came across and the factors that influence the aging of perovskite solar cells. So we use mesoporous devices based on TiO2 compact layer, TiO2 mesoporous, completed with spiral and gold electrode. And we use in almost everything that I'm going to show here, triple cation perovskites containing cesium. And this is the setup we designed specifically for doing aging at EPFL. I'm not going to go into too much detail, but we can control illumination precisely. We can have choice of xenon or LEDs. If we do LEDs, we can have 5 orders of magnitude of illumination control, of intensity control. Then we can control load on the device. We can have 32 devices, each at maximum power point or any other point along the JV curve. We can control the atmosphere. We can combine different gas sources through mass flow controllers to precisely tailor the atmosphere to exactly what we want. And we can also do temperature control. Again, very precisely, the device sits on a Peltier element. We can cool it or heat it up, cycle it. So it's very flexible to do all kinds of different studies. So I'm going to go very quickly through here for this. This is first when we discovered that how much of a difference composition of perovskite can make when we added cesium to the already mixed cation perovskite with metal ammonium on thermamidinium. You can see we can make quite nice devices with the triple cation composition. We can make them reproducibly. So I'm using this composition mostly because we can make them so reproducibly at high efficiencies that it's easy to study stability afterwards. And you can see that without the cesium, the perovskite under rather gentle conditions at nitrogen 20 degrees is already degrading quite a lot. This is under LED as well. When we add cesium, we can improve this quite critically. However, we discovered soon afterwards that if we just heat up the same device at 65, 70 degrees, it degrades very fast, and we identified the cause of this degradation as the gold diffusing from the electrode with its SIMS. This is where we dig through the device and collect the debris of this digging. We found that there is a lot of gold in the heated device, deep in the perovskite, and it destroys the device. So very quickly, I'm just going to mention that we looked at the spiral under the peeled gold electrode. It's completely porous. We tried to fix this problem successfully by introducing chromium interlayer, old trick from the semiconductors industry. It stopped the gold diffusion. It came at the expense of efficiency. It went down from 20 to maybe 15%. So a trade-off. In the next study, we incorporated rubidium into perovskite to improve its photovoltaic performance. And we also included a PTA HTM. This is a polymer. It's much more robust towards gold diffusion. You can see that now at 85 degrees at MPP, under LEDs and nitrogen, we have very stable devices for 500 hours. So very quickly, that was it. And now on to the main part of my presentation. What influences aging of perovskite solar cells? So we try to unravel different mechanisms by investigating stress factors one by one. And I would like to make a clear distinction between intrinsic and extrinsic factors. And extrinsics would be the ones that we can eliminate basically with encapsulation. So that would be oxygen, that would be water, that would be UV light. And of course, these will determine the final stability of a panel that we make with perovskite solar cells. But the prerequisite for the stable panels will be to have high intrinsic stability of the components involved. And I'm just going to say we used a single device architecture, the mesoporous device with triple cation and spiral and gold electrode. And the reason for that was that we wanted to measure maximum number of different parameters rather than maximum number of different architectures. And the study that we did here involved collecting 300 stability curves, so that wouldn't be really possible to do it for a matrix of different architectures. So we started with UV light, or light spectrum, and the shaded area represents the standard deviation. We always try to measure at least 8 devices for each condition to get some statistics. And under white LEDs, you can see that, that's the wrong button, that the devices degrade quite slowly, actually. When we use xenon lamp, the degradation is slightly accelerated, but the difference is not dramatic. It's not like what we've seen Henry showing that the devices die within 5 hours. And the source of light was unfiltered xenon, so it has much more UV light than the solar spectrum. And in a way, we investigated the worst possible scenario because we're using TiO2, which is speculated to degrade the cells a lot. So the message here is that, yes, UV is worse for perovskite than LEDs, but it's not catastrophic. So we did the rest of the studies under LED to deconvolute the UV degradation from the other intrinsic processes. So the next thing we did was light cycling, and we did here around 20 cycles on a device, 6 hours under light, 6 hours in the dark. And as you can see, we see no light fatigue, or light cycling fatigue. The devices always recover following each cycle and don't seem to degrade a lot. The device that was continuously aged eventually recovered most of the lost efficiency when we left it in the dark for, I think, 12 hours in this case. Then the next thing we investigated was the atmosphere. And as you've already seen, when we have just nitrogen, the devices degrade slowly. When we added oxygen to the system, but still dry atmosphere, the devices degraded critically faster. When we added another 5% of relative humidity, we didn't see much difference. Statistically, the curves are very close. However, when we added 100% relative humidity, we see the devices degrade very fast. And in terms of the 3 first curves, in the dark, we don't see this degradation. These are the blue lines. But we still see very rapid degradation in the dark under 100% humidity. So again, the next thing we investigated was temperature. And you see that under low temperature, so 20 degrees or minus 10, the devices don't degrade very rapidly. At 65 degrees, the devices die within several hundred of hours, probably due to the gold diffusion problem. Surprisingly, when we did cycling of temperature between minus 10 and 65 degrees, we found that the device is actually more stable than under 65 degrees continuously. And when we analyzed this curve a little bit, we found that the degradation is sustained only under 65 degrees, while here we see some transient behavior at low temperatures. So the conclusion was no temperature fatigue of our devices. And then coming to the lower device, this was discussed here quite a lot. We again measured many different devices under different low conditions. We find that the VOC kills the devices the fastest with the most limited recovery. JSC and MPP are more gentle for the devices, and they also recover to the very similar values. At VOC, or open circuit conditions, we see that the fill factor and the loss of VOC contributes the most to the observed degradation. And the way, I should have started saying how we did the experiment, we kept those devices under open circuit, short circuit, or MPP, and we periodically measured JV curves. So this is the procedure here. we let them recover for 24 hours. And then I think it's very useful to do this kind of procedure where we combine MPP with periodically measuring JV curves, because basically we can get all this additional information almost for free. However, we have to be careful when we do it because of the hysteresis problem. The hysteresis in this case, the black curve, increases during the measurement. And you see that the curve from the MPP is by no means the same as the backward or forward scan, and actually even not in between, I mean not the average of the two. So we have to be careful what we report and how we report it. So when we measure the devices, and we would call them well-behaved, we often see this behavior, this two regime behavior with the initial fast exponential decay and a slower linear decay. And then if we leave the device in the dark, we see the recovery of this initial part. It's almost complete in most of the cases. Slightly lower on average than this, but still corresponds pretty well. And the question is, of course, going back to what Eugene was telling us, whether T80 parameter, as we are used to defining it, is relevant in this case. I'm not going to try to answer that question, but if we measure the stability under continuous illumination, I think it's important that we try to reach this linear regime, if possible, so continue the experiment beyond this initial exponential decay. And then if we want to estimate the lifetime, we should only look at this linear regime, which is more or less irreversible, and try to calculate T80 based on this. Like in this case, it's around 3,000 hours. So to summarize a little bit what I've been talking about, this is how we decided to implement aging based on our experience and also based on the results that we obtained during this study. We always do it under illumination. This is not to say that dark stability is completely irrelevant. I think it's a very good step towards measuring, evaluating stability of a device, like a dark thermal stress. But for operational stability, we always measure it under illumination, under one-sun simulator. But we find here that it's possible to relax probably to LEDs without changing too much the conclusions of the study. We use MPP. However, we found here that probably doing it at VOC and JSC is a conservative estimation in the worst case. We do it at room temperature for the reason of deconvoluting different degradation factors. But then, most importantly, under elevated temperature to mimic the realistic conditions solar cells have to go through. And we do it under in an environment. And the reason for that, and not doing it under encapsulated devices under ambient conditions, is that we don't want to deconvolute the quality of encapsulation into our result. And I know that flowing the gas, we may remove some of the decomposition products of methyl ammonium iodide, like methylamine iodide. So perhaps the best way eventually will be to age encapsulated devices in inert atmosphere to deconvolute all the parameters. That's something we have to find out. So to conclude, I've shown you that perovskite composition and device architecture can have rather critical influence on stability. We think aging under light, maximal power point, and then at room and elevated temperature is the most reliable way to assess operation stability. And we think that aging standards are urgently needed to help the field forward. And I just want to add that we also think that a similar study that we did, done on many different architectures, so kind of creating the matrix of different architectures and all the different conditions studied, could be very useful to eventually look at understand which parameters are critical for perovskite solar cells, and then to discuss the standards that we have to develop. So I'd like to finish with an invitation for you to try to do similar studies, maybe for different architectures, and then we could understand a bit more systematically what is degrading perovskite solar cells and how to go about it. Thank you.
Great. Thank you very much, Konrad. Okay, we have got about 10 minutes for this questions session. I see Eugene already raising his hands, and I'll pass that.
First of all, thank you very much for all of you for very good talks, which generate a lot of questions, may generate, but I will ask only two, one Konrad and one for Beatrice. Konrad, what is your explanation about the bias effect? Why in OC, we all see it, why the degradation in open circuit is higher than short circuit?
So while we didn't really investigate it in detail, you see, like we just scratched the surface. We tried different parameters and just see this is what we see. We think there might be some mechanism which is related to the very high charge density at OCV. Because of course at OCV you don't extract the charges from the devices. Everything that's generated has to recombine. Maybe it recombines somehow through defects. We have a lot of excited electrons that can maybe damage perovskite, but this is my speculation.
Yes, thank you.
Yeah.
And,
Very simple one. You show the effect of temperature of different perovskite solar cells and the initial efficiency. I mean, I guess you use a very high efficient solar cell, and the efficiency you report initially is the one in that temperature. So the efficiency was 20, like 15 and 9, like 15. It went down to 15 at minus 10.
So we were discussing yesterday that good cells are usually stable, and for that reason, in this study, the past qualifications to be included was at least 17%, and we needed 300 devices at least to destroy, so we couldn't keep the bar higher. Most of them are around 20 to 18%, 21 to 18% devices. And yes, this is initial efficiency. Of course, when we lower the temperature, we freeze the spiral a little bit, we lose a lot of fill factor. That's why they perform lower. When we heat them up, they lose VOC on the other hand, so they also perform a bit lower. So the temperatures for those particular devices, the initial efficiencies were higher, above 17%.
Okay, I've got one final question here. So,
Hi, I have a question for Konrad. When you say, first, I think I understood right, when you say you keep it at maximum power point, you're also measuring every 20 minutes JV curve. Is that what you said?
Yeah.
Okay,
that's our standard procedure.
When you say maximum power point, that means you keep it at maximum power point voltage, or you do maximum power point tracking?
We always do maximum power point tracking.
Tracking as in stepping tracking, or?
Like with a perturb and observe method. So we would first measure the JV curve, and then we would start tracking from the maximum power point voltage measured at the JV curve, and then we would go 10 millivolts higher, then that voltage measure efficiency, then 10 millivolts lower, and we would decide, okay, which of those 3 points is the highest, and there we move, and then we do another iteration and like.
And what's the delay that you use there?
1 second.
Okay, thanks.
okay, so please join me in thanking all the speakers for their talks.